Hello, today we have this problem, and the main issue with it is that we have the concept of graph introduced, and we don't have a norm defined for it, which is a problem, and I couldn't wrangle around it in any way. So I have a band-aid solution. I'm gonna not define the norm of it, but I'm gonna say that whenever we take a function, let's call it g of x, that maps x to x f of x, then the limit as p approaches x of g of p is going to be equal to the point where the first component is the limit as p approaches x of p. The second component is the limit as p approaches x of f of p. This is necessary because we're not given a norm and we're not working with real numbers. We only said that, well, if we're to take the real numbers, then we will be working with a plane, but it's not necessarily real numbers. So we have this concept of graph here, which is just points of form x f of x. Have to prove that if E is compact, then if E is compact and f is continuous on E, then graph is compact, and vice versa. It's if and only if. So the way I'm gonna review it is on case-to-case basis. So the first one, let's say that f is continuous. Well, then what we can say is we can go ahead and work with g of x. We're to take a limit of g of x for some arbitrary point p, so p belonging to E. And next what we're gonna do is, actually not p, it's occupied by the argument for the limit, okay, like that, for x belonging to E. And for this one, this is gonna be just x, and the reason it converges is because x belongs to E. Otherwise it wouldn't, even though it will be a Cauchy sequence. And for the second one, well, since f is continuous, now this is going to be f of x, which is going to be equal to g of x. And this together implies that g is continuous function. So g is continuous. Well, what does it mean? That means that if we were to take compact space and fit it into G, then the resultant space is also compact. So that's the first case. Now the second case, which is arguably more troubling. Suppose f is discontinuous. Well, then it's more complicated. Essentially, we're to take f of x and it's discontinuous, and then there must exist some point x belonging to capital E where there's a discontinuity which is characterized by either the fact that we have something unbound going on, but it can't be unbounded because E is compact, and we're to take, okay, let's say that f of E capital is unbounded. Well, that would actually imply that g of E is also unbounded. Now, again, I'm making assumptions that is related to the fact that I'm not given the norm of the graph. So, complaint, Mr. Boulder, rooting for that. which implies that G of E is not compact. So that's the case 1. Next case, where it is bounded, we say that the limit... Okay, let's first write down that this is an x such that limit p approaches x of p doesn't exist or not equal to f of x. So the second part, let's say that it does exist. P approaches x, f of p equals to some p not equal to x, not equal to f of x. Well, then we have a trouble, because if we were to take g, say let's take a limit as p approaches x, g of p is gonna be equal to x comma p. And mind you, if we were to take g of x, gonna be equal to x f of x. So this over here is a limit point of g of e. However, the trouble here is that it doesn't belong to g of e, because there's it's already occupied by this part over here. So doesn't belong. And the issue here is that, well, if g of e was compact, then it would also be closed and bounded, and if it were closed, then every limit point would belong to g of e, so g of e isn't compact. And finally, we have the last case, where it doesn't converge to anything. Well, recall how it's bounded, and that implies that if it doesn't converge to anything, then there are multiple limit points. And we're coming back here. There are multiple limit points at the same first component. Then, well, one of them does not belong to g of e. So we just return back here. It's oversimplified, and also I miss a lot of rigor. Primarily because if we were to look at the graph, then it's properly defined only when we look into R, then it is obvious that the graph for R like this is just R squared, for which we have a very well-defined norm. This will be just 2D plane. Again, sorry, maybe there is a way to solve this without including the notion of norm that I'm not aware of. You can comment about that. I would absolutely not mind that. I actually would be very positively surprised, because this channel is mostly about me learning, not the viewers. I wouldn't pose this as educational, because I often make mistakes. So this is for today, yeah? Thank you for watching. Bye.